Okay, today I'm going to take the most recent full-length practice test released by College Board. This is the 2019 multiple choice practice exam for the international practice exam. That was released with probably the most realistic questions you could expect to see on the AP exam. The format is the exact same as you would expect to see. We have 50 questions to do today, and they give you an hour and 30 minutes, 90 minutes to do those questions. So you're looking at almost 2 minutes per question, between 1 and 2 minutes as you go. As you take the test, you'll get this exact periodic table, so you know what to expect. This periodic table doesn't have things that I would have you put on yours in class, like oxidation states, like 1 plus, 2 plus, 3 plus, etc. It doesn't have periodic trends on here. It doesn't have orbitals. So you get a blank periodic table. You also get the same formula sheet we will use in class. Everything's kind of the exact same here. All the sort of different formulas on the left, and on the right what the units stand for there. So a couple pages of formulas we'll use as we go through the test. Today I'm going to take the multiple choice section. I'm going to go through and explain my reasoning for why I choose all the different questions as we go through. I think you'll find that the questions are more reasonable than some of the ones I've been giving you in class to review. A little bit less tricks and stuff like that, but it is still difficult. You have all these different sections put together. All right, so we'll go through them. It's going to take a little bit. I do have all of these questions on AP Classroom. You can access this exact same practice test we're going to take. So if you would like to take the test first, then come back and look at this, or jump around, or however you want to do it, it doesn't really matter to me. Whatever you think is best for you. So I'm going to go through the questions as well as I can in order. I'll do my best to be thorough and explain why I'm doing what I'm doing and kind of how I would break down and solve each of these questions. So starting number 1, in which of the following processes would S be negative? So S is entropy, right? How random something is, right? And all of these things are reactions turning from like a liquid to a gas, or a solid to a liquid, solid to gas, gas to liquid. Okay, and in general with entropy, it's a measure of how random stuff is how you can kind of think about it. So things like solids are very ordered, right? They have very specific patterns, right? They will have a very low entropy. They're very organized. They're not very random at all. Whereas liquids, they're moving around, so there's a bit more randomness. They're bumping into each other a little bit wildly. So there's like a little bit. They're kind of medium entropy, but gases have the most. Gases are basically not bound by intermolecular forces in any way. They can travel around to fill up their room randomly. They have the most entropy. So entropy being negative means entropy has to go down, meaning I'm getting something that has less entropy, which means I'm going from a gas to a liquid, or a liquid to a solid, or a gas to a solid. Answer here is D. Going from Cl2 gas to liquid is making it have lower entropy. But if you get confused which way is which, you can kind of play like which of these is not like the other. Liquid to a gas, it's getting hotter, it's getting more random. Solid to a liquid, it's melting, it's getting hotter, it's getting more random. Solid to gas, same idea. This is the one that sticks out. I'm cooling something off to make it more, give it less entropy. All right, number 2. Of the 3 solutions listed in this table, so we have 0.1 molar acetic acid, 0.1 molar Ki, some potassium iodide, 0.1 molar of CH3OH, methanol. Of the 3 solutions listed in this table, which one has the greatest conductivity, electrical conductivity? Which one conducts electricity the most? Anytime you're dealing with conductivity, you're looking for ions, positive and negative charges that will allow electrons to travel through a solution. So all of these are going to be dissolved in water. Which of these make ions? So first of all, I can kind of look at the type of bonding. The first one is an acid, so this will split into some H plus and some H2C3O2 minus. But because this is a weak acid, only a little bit of this will split apart. So when I dissolve this acid, only maybe 1% of this actually splits into its ions. The second one here is Ki. That's just an ionic bond. That is a salt. When I take this and put it in water, the whole thing essentially should split apart because K is one of the substances that makes salts really good at dissolving. K, potassium, sodium, nitrate, or ammonium will help the salts dissolve. So this one's looking good because it makes a lot of ions. This last one is a covalent bond. I have all nonmetals here. So this will not dissolve and split apart into ions. This does have a hydrogen bond, which will allow it to interact with water a little bit, but of these three, this one in the middle will be the best at conducting electricity because it produces the most ions. So our answer is going to be B. Ki, because Ki completely dissociates to produce ions. All right, 3. Hydrogen gas reacts with iodine gas at a constant temperature in a sealed container. Sealed, rigid container, doesn't really matter. That just means a container with no holes in it that's not going to break or change shape. Nothing we have to worry about. The gases are allowed to reach equilibrium according to this equation. Which of the following best describes what will happen to the reaction immediately after additional iodine gas has been added? So I'm adding iodine gas to the system, which is, according to Le Chatelier's principle, going to shift the equilibrium to the right. The system is going to try to counteract the change we made to it, so it'll try to get rid of that I2 we added by going to the right. And so that means the right reaction will speed up, which would be answer choice C. The rate of the forward reaction becomes greater than the rate of the reverse reaction. All right. Number 4. The first 5 ionization energies of an unknown element are listed in this table. So this is a very common table you'll get. Ionization energy is how much energy it takes to lose an electron, and what you're always going to look for is where this spikes significantly. So I go up a little bit, I go up a little bit, but here is where I notice I jump significantly, like from 4 digits to 5, like a whole order of magnitude up. This is by far kind of that biggest increase, right? I'm adding like 1,000, add like 1,000, add like 8,000. So something here is what I'm looking for between the 3rd and 4th energy level. So my energy jumps. So all 3 of these must be easier to remove valence electrons. And then anything after that will be a core electron. So I haven't even read the question, but which of the following statements correctly identifies the element? It's going to be something with 3 valence electrons, and that'll be B. Aluminum, because of the large difference between the 3rd and 4th levels. All right, number 5. The diagram below represents a particle in an aqueous solution. So we have some sort of particle, and we have some water molecules surrounding it. Which of the following statements about the particle is correct? Okay, so what I'm thinking before I read my answer choices is, why is the water facing this way? These are the hydrogen ends. The hydrogen ends have a positive charge. You notice all the positive charges are facing this center ion, which tells me they're attracted to it because it's negative. If these water molecules are flipped around, I would know this is positive. So that's probably what the answer is going to have to deal with. And answer choice B, I think, says this. The particle must be an anion. Remember, anion means negative charge because the positive end of the water molecules is pointed towards it. You don't remember which ends are which in a water molecule, right? What I'm looking at is their electronegativities. So I could reference my periodic table. Electronegativity generally increases as you go up into the right, and oxygen is like the second most electronegative element, right behind fluorine. Right? So that just means it's going to take the electrons a little bit more. The oxygen side will be negative, and both of the hydrogen sides will be positive. This is that partial symbol we can draw. All right, next, number 6. A student obtains a mixture of the liquids hexane, C6H14, and octane, C8H18, which are miscible in all proportions. That, remember, just means you can mix them together. Which of the following techniques would be the best for separating two components of this mixture? So if I take these two similar liquids and mix them together, how would I separate them? There's a couple ways to separate things. And all the answer choices here are kind of different ways you could do it, but there's some information given to us on the table. The density over here looks like these numbers are really close. Sometimes it's possible to separate things by their densities. When something is really dense and something is not very dense, one will rise to the top and one will filter down to the bottom, and then you could separate them using a separatory funnel. But the thing that is significantly different is their boiling points, right? This one down here, hexane, is going to boil a lot faster. So if I take both of these and put them under a flame and heat them up at the same time, all the hexane is going to turn into gas and boil away well before the octane does. And that is called a distillation. Answer choice D, because the liquids would boil at different temperatures owing to the differences in the strengths of their IMFs. Octane has more intermolecular forces because it has more London dispersion forces, which is why its boiling point is higher. All right. Number 7. The value of the equilibrium constant for this reaction is 1 times 10 to the 10th. So it's telling you the capital K is 1 times 10 to the power of 10. That means this reaction happens really strongly. It's very product favored. This reaction would happen mostly to the right. All right. What's the value of the equilibrium constant of this reaction? So I have a similar reaction. I have flipped it and doubled all the numbers. So we have to remember what to do to a K when you change it around. And the K, the equilibrium constant, is the weird one. This isn't like Hess's law with enthalpy. This isn't like reaction rates. This one kind of works its own way. If you flip a reaction around, you don't make this negative. K will never be negative. Instead, you take the reciprocal. So because I flipped this reaction around, I'm going to take the reciprocal. And because I doubled everything, I'm not going to double my answer. I'm actually going to square my K. In the order of operations I do this doesn't matter. I can do 1 over K and then square it, or 1 over K squared. I'll get the same answer either way. So I'm just going to plug in how I would write it. My K is 1 times 10 to the 10th. And then I'm going to square it first. And then 1 divided by that answer. I'm going to take the reciprocal. 1 times 10 to the negative 20. Answer choice A is my answer. All right, 8. To catalyze a biochemical reaction in an enzyme typically. Okay, so this is question basically more of a vocab question asking you what does an enzyme do? The purpose of an enzyme is to speed up a reaction, to make it happen faster, right? And how it does that is by lowering that activation energy. That's the key idea with an enzyme, right? The activation energy of a reaction is how much energy you need to put in extra before the reaction starts to kind of make it go. It's like that roller coaster hill. You have to build up with enough energy to get over there before you can get to the drop. And an enzyme, all it does, it gives it a separate pathway that lowers that amount of energy you need to start. So our best answer choice here is going to be B. It binds temporarily to reactant molecules. That's very sciencey, but to lower the activation energy is the keyword I'm looking for. Number 9. Of the following diagrams, which best represents the solid structure KF? So KF, I have a metal, non-metal. This is an ionic solid. So what I'm looking for anytime I have an ionic solid, an ionic bond, is that lattice structure. Positive, negative, positive, negative, positive, negative. And it'll go down as well. Negative, positive, negative, positive. We want that checkerboard shape. The only one here that represents that is B. And that's specifically, I kind of glanced over this because it said solid KF. When it's solid, it'll look like this. If it said aqueous KF, then actually you would choose D. But this is what you're looking for a solid. It has that lattice structure. All right, 10 and 11 both use this diagram. We have a voltaic cell. Okay, the standard reduction potentials for the half reactions associated with the electrochemical cell are given in this table. Okay, so it looks like I have silver plus an electron giving me regular silver, this silver ion. Zinc plus 2 electrons gives me zinc. It also gives me their cell potentials over here. And if we kind of remember, when we make a battery, we're looking at our two reactions, the smaller value, the one that is lower, and if it's negative, the more negative one is the one that gets flipped around. So this reaction here will become positive 0.76, but we're going to make it our oxidation. Every battery that we're going to look at is a reduction and an oxidation. This is my reduction reaction. This one I'm going to flip around to make my oxidation. And when I do that, I flip my voltage to the positive number. Remember, gain electrons reduction. This is written by gaining electrons. So this normally is my reduction reaction. That is going to stay that same value. Your lowest one is going to flip around backwards to turn it to an oxidation. I am making electrons a product because I am losing electrons. Oxidation. If I wanted to write my cell potential, now I can add these two values. 0.8 plus 0.76, to get 1.56. I didn't even really read my question yet, but that's kind of always what they're asking here. And that's actually number 11. 1.56 is the voltage of this battery between these two things. So when you're looking at your reactions, flip the smaller one around and then add them together. I skipped over 10 though. It says, which of the following is the net ionic that occurs between these reactions? So basically, what is the overall reaction if you add together these half reactions? The trick here is when you add them together, electrons cannot be in the reaction anywhere. So like answer choice B, for example, I know can't be right because it has electrons as a reactant. And same with answer choice C, has electrons as a product. Electrons cannot exist solely by themselves. They must be attached to something. You can't just have a free-floating electron around. So I know it's either A or D just from knowing that electrons can't be written. And so what I need to do is balance these a little bit just so the electrons will cancel. The bottom one is 2 electrons, the top one is 1. So I'm just going to double everything in this first reaction to give me 2 Ag pluses plus 2 electrons, gives me 2 Ag solids. Then my electrons can cancel. So my answer choice that matches that idea is D, with the 2 in front of the Ag because I had to double it to double my number of electrons. Those are the two most common things asked about these voltaic cells. All right. We have a chemical reaction given to us. Chemical reactions are needed a lot of the time, but I don't like to start by reading it because it's kind of a lot to comprehend. So I'm just going to kind of contextualize this as I read through. In a one-person spacecraft, an astronaut exhales 880 grams of CO2 per day. To prevent the buildup of CO2 in the spacecraft, a device containing LiOH is used to remove the CO2. Okay, so that's what this reaction up here is telling me. I take CO2 and add some LiOH, it's going to get rid of it. Okay. What mass of LiOH is needed to react with all the CO2? Okay. So this is going to be like a train track problem. Right? I have 880 grams of CO2 per day, and I would need to see how many grams of LiOH I need to react with that fully. So I'm just going to do a train track converting grams of CO2 into grams of LiOH. So 880 grams of CO2. I'm going to convert this to moles. Grams of CO2 on the bottom. It told me its molar mass is 44 grams per 1 mole. I always go to moles first because I need to swap from CO2 to LiOH, and I need a mole-to-mole ratio to do that. All right, moles of CO2 is now my unit. Put it on bottom to cancel. Put moles of what you're looking for, LiOH, on top. My mole-to-mole ratio here is when I need my chemical reaction. All right, how many moles of lithium are needed for every mole of CO2? 1 mole of CO2 requires 2 moles of LiOH. But now I need to convert that back into grams. Moles of LiOH on bottom. Turn it into grams. I need to use its molar mass. It gave me that somewhere in the problem as well. Molar mass is 24. So I have some numbers that work out pretty nicely, but we just throw it in our calculator. The numbers will work out well because you used to have to not have a calculator for this section. So you could have divided this to get 20 times 2 and then times 24, which wouldn't have been as bad to do, but you get 960. Answer choice D. All right, 13. We're wasting lots of paper today. That's okay. All right, the data from the study of a decomposition of NO2 to form NO and O2 are given in this table. Which of the following rate laws is consistent with the data? Okay, so what I'm looking at here is I have time, I have the concentration of NO2, the natural log of NO2, and 1 over NO2. Hopefully this looks a little bit familiar because this is how we test to see what order a reaction is. If you graph the time versus NO2, and it is a completely straight line, completely linear, then my reaction is 0th order. If I graph the time versus the natural log of NO2, and it's a completely straight line, my reaction is 1st order. And if I graph time versus 1 over NO2, then my reaction is 2nd order. And I would recommend just kind of remembering that. You can derive this, but you need integrals and calculus and stuff. So it's easier just to kind of remember. Fortunately, they're in order, and I have to remember which one's which. Now, you realistically, the expectation would be to graph this, but that's a lot of work when you have less than 2 minutes per question. So what I'm going to do is this goes up by 100 every time, right? It's nice and even. So what I'm going to look for is another column where all the numbers change by the same amount every time. So if this changes by 100 and this changes by 5, this changes by 100, this one changes by 5, that's how you know it's linear. So that's a way you can check it. So I'm going to do my first column here, 500 minus 0.500 minus 0.368. That's a 4. That's a 1. Okay, that's what I meant to say. It goes down by negative 0.136. I'm going to see if that trend continues. 0.364 minus 0.286. No, this time it goes down by only 0.078. So that's not decreasing linearly. So I know it's not that. Second one, I'm going to check the same thing. I'm going to see if this value changes linearly. I can already kind of tell it doesn't because this one's about 0.4 and this one's only about 0.2. But let's check the last one. I increase by 0.75, and then 0.75, and then 0.75. So that one is linear. So this is a 2nd order reaction. They're trying to get you with answer choice D. It's not answer choice D because that would make sense. This is just telling you, it doesn't tell you that this is the rate law. It's telling you it's a 2nd order reaction. 2nd order. B is the answer. All right, 14. The photoelectron spectra, the PES, for H and HE are represented above. Remember, on a PES spectrum, the height of a peak is the number of electrons you have. So when I'm looking at these, it looks like hydrogen has less than helium, which makes sense based on what I know about those guys. And then on the axis here, the x-axis, you have energy or binding energy. It's just how strongly these electrons are attracted to the nucleus. The more this peak is to the left, the tighter the bond the harder they are to remove because they're more bonded to that nucleus. So I have both of these photoelectron spectrons to compare. Which of the following statements best accounts for the fact that the peak on the helium spectrum is further to the left? So why is this further to the left than hydrogen? And why is it taller? And that's kind of what I was talking about. It must be further to the left because the binding energy is greater, at least a little bit. That means helium's electrons are harder to remove because they're closer, or not necessarily closer, they are, but because they're harder to remove for whatever reason. And then there also are more electrons because it is higher. So the answer choice here that has both of those things is B. Helium has a greater nuclear charge than H. So that's saying it's more attracted to the nucleus. The nuclear charge is greater. And an additional electron in that same energy level. Okay. I know I'm not reading through all the answer choices and stuff. I'm trying to go relatively quickly and just kind of show you my train of thought as I go through these questions. The next 5 questions all use this information here. I have a chart. I have a compound ethane and propanol. So what I'm looking at first thing before I get into reading any questions is kind of comparing these in my head. They both have a bunch of CH bonds, but I noticed this one has an OH bond. OH is a hydrogen bond, so I'm sure that's going to come up somewhere in the question. Right? I also have some unknown compound. That'll probably be a question at some point as well. I have the molar masses of these two things. It looks like propanol is about twice as big, which makes sense. And then they give me a balanced equation for this reaction. This is kind of something weird you might not see usually, is they have a fraction for moles. You can do that, I guess. Normally we would write this, we would just double everything else, and then it would end up as 2, 7, 4, 6, but this is technically another way you can write it. And the last thing over here is the enthalpy of combustion, how much heat is released when these reactions occur. The negative sign is how I'm figuring out it's released. Negative means exothermic, it's being released to the environment. All right, so let's use this for the next couple of questions. 15 says, which of the following is the molecular formula of the unknown? Okay, well, how would we know that? How do we know what the unknown is? It doesn't give us its weight, but it does give us this reaction. So what I'm going to do, I know basically how much of everything else it's balanced already, which is kind of a weird backwards way, a neat way to problem solve it. But what I can do is on the left side, I have 4 carbons. So the right side must also have 4 carbons. So I know it's going to be C4. Right? I also have 4 H's times 2 is 8. So I have 8 H's as well. And you can kind of see the answer choices are matching that, right? C4H8. It does look like it can't be C, because that one has 4 H's only. Now the last thing I need to add up is the O's. I have 4 and 2 is 8, plus 4, I have 12 O's. But on this side, I already have 10, so the last 2 must come from my formula here, which will give me answer choice D, C4H8O2. Not a problem we normally would do, but kind of a creative sort of balancing problem to do there. 16 says, which of the following best explains why the combustion reactions represented in this table are exothermic? So why are these reactions releasing heat? So the idea is a chemical bond, it takes energy to break those bonds. So if I only look at the left side of a reaction, so I'm just going to use this top one for an example, I have to add energy to break all of those bonds. I have a carbon to carbon bond and 6 carbons or hydrogens bonded to carbons. I have some oxygen bonds. I have to add energy to break all of that, right? So I have to input a certain amount of energy. Typically this would be like activation energy. But on the right side, I get to form a bunch of new chemical bonds, and forming a new chemical bond releases energy. All of this energy I'm saving by putting my atoms in more energy efficient arrangements gets released back to the environment. In an exothermic reaction, the amount of energy you produce is just outweighing the energy you had to put in. That's why this overall answer is negative. It's because reforming all these new bonds releases more energy than I had to put in to break them all in the first place. An endothermic reaction is just opposite. I have to add more energy than I actually get out from reforming all the bonds. So my answer choice that's going to match that the best is D. The energy required to break the bonds in the reactants is less than the energy released in forming the bonds of the products. All right. Next question here, ready? I still need this chart. Based on the structural formulas, which of the following identifies the compound that is more soluble in water? And helps to explain why. So this one's only looking at ethane or propanol. So these two. Which of these would I expect to dissolve more in water? So what I remember is polar things like water are good at dissolving other polar things. Things with hydrogen bonds, things with dipole-dipole forces, and that one looks like propanol. This is where this H bond's going to come into play. Propanol will dissolve better in water because of the hydrogen bonding, and the answer there that matches is D. Propanol, because its molecules can form hydrogen bonds with water molecules, but those of ethane cannot. 18 here. In an experiment, 30 grams of ethane and 30 grams of propanol are placed in separate reaction vessels. Each compound undergoes complete combustion with excess oxygen. Those two sentences are very heavy in like chemistry words, but like basically we're taking 30 grams of this and burning it, 30 grams of this and burning it. The fact that they're in vessels or undergoing excess oxygen, complete combustion, that's just saying everything is normal. I'm burning all of these. Which of the following best compares the heat released by each combustion reaction? So if I burn 30 grams of this, 30 grams of this, which one makes more heat? So the trick with this one is, over here I have the heat released. So if I had an exact equal amount of these two things and burned them, I would expect propanol to be the answer because it releases more heat per reaction. But I have to be very careful because ethane and propanol don't weigh the same amounts. So when I give you grams of each one, I can't directly compare them. I have to use moles of each one to compare them. The enthalpy is the kilojoules per moles of reaction, not the kilojoules per gram. So what I'm going to do is take that 30 grams of ethane and convert it to moles. Well, ethane has 30 grams per mole, so that number was chosen very intentionally. That tells me I have 1 mole of ethane. I have, in the problem, 30 grams of propanol as well. But propanol weighs 60 grams per mole. So when I divide it by 60, I only end up with half a mole worth of propanol. So if we apply that to the rest of the question, when 1 mole of this reaction occurs for ethane, 1560 is released. So this equals 1560 kilojoules of heat released. And when half a mole of this breaks, that's only this number divided by 2. Only 10 kilojoules is released. What that means is the amount of heat released by 30 grams of ethane should be greater than 30 grams of propanol. So C is the answer. That's a pretty tricky question, though. Okay, and we'll use this information one more time. A sealed 10-liter flask at 400 Kelvin contains equal molar amounts of ethane and propanol in gaseous forms. So this time I have the same number of moles. Which of the following statements concerning the average molecular speed of ethane and propanol is true? So basically I just want to compare how fast these things are when they're gases. Essentially all we need to know for that is, since they're at the same temperature and they're the same container and everything like that, I just look at how big they are. Bigger things are slower, smaller things are faster. So I'm expecting ethane to be faster because it's smaller. My answer choice that matches with that is B. The average molecular speed of ethane is greater than the average molecular speed of propanol. All right. Number 20. A sample of potassium nitrate, solid, is stirred into water at 25 degrees Celsius. The compound dissolves endothermically, so I have to add a little bit of heat to make it dissolve. Which of the following best helps explain why the process is thermodynamically favorable at 25 degrees Celsius? Okay, so it seems like the problem here is kind of at odds with itself. I have to add heat to allow this to actually dissolve all the way. Okay, so this isn't going to dissolve without me adding heat, which makes it seem like it's not thermodynamically favorable, because remember, this is just another way to say spontaneous. But this is telling you it actually is spontaneous, so how can we justify that? Remember, spontaneity is G, Gibbs free energy, which does depend on if it's endothermic or exothermic, right? If G is negative, it'll be spontaneous. In this case, H was positive. H is endothermic. So it feels like, oh, G should not be negative. But there's another term here, temperature times entropy. If entropy goes up, this will be subtracting a large number, which can overall override this positive H to make G overall negative. So I also have to think about entropy. And if I'm taking a salt, which is a solid, and turning it into aqueous, which basically means liquid, entropy is increasing. So that is explaining why this can still be spontaneous even if it's endothermic. Right? And our answer choice that matches with that is D. Dissolving the salt increases the entropy of the system. All right. One more thing about that, I guess. The entropy naturally wants to increase. So the entropy of the universe is naturally towards randomness, towards things being in disorder. All right, 21. A solution is prepared by mixing equal volumes of 0.2 molar acetic acid and 0.4 molar sodium acetate. Which of the following correctly describes what occurs if a small amount of HCl or NaOH is added? So here I have some weak acid and its conjugate base. That is a buffer. The purpose of a buffer is to resist a change in pH. The pH will change a little bit, but not dramatically. Because I have a little bit of acid, I have some H plus available to react with any new base that I add. So if I introduce some new OH, there's already some hydrogen in my system to be able to react with that. On the flip side, if I add any hydrogen to this, I have my conjugate base ready. My conjugate base is ready to react and interact with any hydrogen that's introduced, any acid that's introduced. So my buffer can resist a lowering of pH. Right? If you add an acid, you lower the pH because it has the conjugate base. It also can resist a raise in pH because it has H plus there to resist a base being added. And I just have to pick the answer choice that matches with this idea here, which can be kind of hard to read through. Our answer is B, though. If HCl is added, so if H is added, the pH will decrease, it will get lower, only slightly, because the H plus ions will be able to react with the C2H3O2 ions. Right? The H plus ions will be able to react with the conjugate base I already have. All right, 22. Long question here, like lengthwise long. A mixture of H2 gas and O2 gas is placed in a container represented above. So H is the darker color. I have 4 H2 molecules and I have 4 O2 molecules. The H2 and O2 react to form H2O. So I take H2 and O2 to form H2O. Now I do need to be careful. This isn't balanced fully. So I need to put a 2 here and a 2 here. So I'm going to need 2 hydrogens to react with every oxygen to make my water. Which of these boxes represents what I would expect to have left? Okay, so when I think about it, not all of these are going to be able to form water. I need to use 2 hydrogens to make this reaction into 2 waters. I only have 4 hydrogens to use. So I'm going to use all 4 of my hydrogens, so none of this will be left over. But my oxygens, I'm only going to have to use 2 of them, right? I can only use as many as I have hydrogens. So I'll still have 2 oxygen molecules remaining in my solution, right? And for H2O, I was able to make 2 full molecules of that as well. No, hold on. So able to make 4. 4 would be the maximum that I can make. Maybe that's not the best way to kind of think about it. You can kind of match everything here. So you can do an H and an H. These 3 things is an H2O. And I can kind of do that again. This is an H2O. This is an H2O. This is an H2O. I have 4 H2Os, 2 leftover O2s. B is the best answer. So maybe thinking about the particulate like this, kind of matching the things together that will go together, is a good way to think about what it's going to look like afterwards. I like that better than trying to add it all up like that. All right. 23. After a certain pesticide compound is applied to crops, its decomposition is a first-order reaction with a half-life of 56 days. What is the rate constant for this decomposition? We haven't had to do this a lot yet, or at all yet, but I have my formula sheet. So I'm going to go find the kinetics section down here, because this is where all of my reactions are. Now, okay, they only have one of these on here now. This reaction here, I'm looking for the half-life formula, which is this one right here. The time of a half-life is 0.693 divided by K. What I was expecting to see, and if I wasn't sure, I have that over here to look at as well. It tells me K is the rate constant, T 1/2 is the half-life time, so all I have to do is do 0.693 divided by K. What they don't have here is the first order half-life, or the second order half-life, which is a similar formula. That's the one that's like 1 over K, not 0.693 over K. It's 1 over K times the concentration of A that you start with. But that's not on the formula sheet anymore. So this is for second order only, but that's not provided. So we're only going to have to worry about this one. Okay, put that to the side. All right, so I'm going to write down that formula. Time of a half-life is 0.693 over K. Where that 0.693 comes from is more like calculus magic, but it is the ln of 2. That is the number on top, so it's not a completely random number. All right, so I'm going to plug in, has a half-life of 56 days. So I'm going to plug in 56 for my half-life, and now I just got to solve for K. K is that's what I'm looking for. So multiply K up here to get 56 equals, not get in the way of the next problem, we'll need that space. So 56K equals 0.693. K equals 0.693 divide by 56.012. That's my answer. Okay. 24. Which of the following can be inferred from the diagram above that shows the dependence of potential energy on the internuclear distance between the two atoms? So this sort of graph we've seen a few times. I have on my x-axis the internuclear distance, which basically means I have two atoms, and this is how close they are to each other, the radius between their nuclei. They can't overlap, which is why as you go further and further to the left, these numbers will eventually approach infinity, because these things cannot completely overlap on each other. Over here, I have the energy that you save or use. If the number is positive, you have to add that extra energy to push them together. For example, if you want to push these things too close together, you have to actually apply energy to do that. But if they're at the perfect distance away, the sweet spot here, they actually save energy. The chemical bond, because of all the attraction between the protons and electrons in the adjacent atoms, it actually saves energy overall. The absolute minimum value is where the bond will normally be made. So this exact minimum value, which is at about 75 picometers away, is where they will actually bond. So my answer here is B. The atoms form a bond with a bond length of 75 picometers. That minimum energy is where they will bond. That is the most energetically favorable bond they can make. All right. A mixture of two gases, 0.01 mole C4H10 and 0.065 moles of O2, is pumped into a cylinder with a movable piston as shown above. So I have gas, but I have two different gases in here. Right. The mixture originally at 200 Celsius and 1 atm is sparked, and this chemical reaction occurs. So I had this and this in the piston. I made the chemical reaction happen, and we're going to make this and this. Which of the following is true about the product gases, which of the following is true after the product gases return to their original temperature and pressure, and why will the change occur? We assume all gases behave ideally. Kind of a weird question, but you're taking two gases and you're mixing them together and then making them react. The main thing that actually changes is over here on the left. If you add up your total amount of gas, you have 15 moles of gas. 2 and 13 together. It doesn't matter what gas is which, because the gases will just expand to their container anyways. Over here, I have 18 moles of gas, right? This has more moles of gas, so I'm expecting the pressure will be higher as a result of that. Answer here is like, what will be the cause of that, or what will affect that? So this will have a higher pressure, which means the gases are pushing more on the sides of their container afterwards, which means because this piston can move, it's going to be pushed a little bit up by that increase in pressure, which is answer choice A. The piston will be higher than its original position because the cylinder will contain a greater number of gas molecules. All right, so I'm going to take a little break here. That's the first 25 questions. The next 25 will be coming in a new part that I'll post on the channel later today or the next day. Okay, so hopefully that was helpful, and I'll be back with the rest of it soon.